Hello, welcome to lecture 3 of electronic devices. We are still in module 1 and in this lecture I will touch upon certain more important topics which are important rather from the point of view of explaining the physics of semiconductor devices. So, what I will do is that I will first describe or I will just first give a brief review of a very important theory which is called quantum theory, which is essential for understanding the physics of semiconductor devices, right, which is the main aim of this course. For that we need to have a brief review of quantum mechanics, which you have already learned in the portion of physics. Okay. So, let us directly go to the lecture without wasting time. All right. So, review of quantum mechanics. Well, the world around us that we see, that world is called the macroscopic world. That means, everything that we see around us is macroscopic in nature according to us, and whatever phenomena or observation that we see in the macroscopic world can be easily explained by Newtonian mechanics or classical mechanics. Okay. But the observations or the phenomenon that happen in the atomic scale or in the atomic world, that actually cannot be explained by classical mechanics. Okay. Now, it is very easy to understand classical mechanics because we observe it around us every day. Okay. Quantum mechanics is something which we are not very much used to in our daily life. So, what we do is that at the beginning we find it a bit awkward to learn about quantum mechanics. Here we will only give a brief review of what it actually is. Okay. So, basically if there is any observation in nature which cannot be described by the existing laws of physics, okay, then what is required is we need to establish absolutely new laws to explain the cause of a phenomenon that is happening. Because if you cannot explain something based on the existing laws, that means there is something which is in nature that has still not been recognized by science. So, therefore, we need to establish new laws for them, and that was the result when quantum mechanics was born. Okay. So, in order to explain the natural phenomena on the atomic scale, we actually need the help of quantum mechanics. That is the basic idea behind quantum mechanics. Now, just now as I said that the development of this quantum theory was mainly due to the series of experiments by eminent scientists, okay, like Einstein, Young, okay, etc. So, first let us come to the portion of photoelectric effect, then Young's double slit experiment, and then the atomic spectrum. Now, this photoelectric effect, it illustrated beautifully the particle nature of light, and this was developed by Sir Albert Einstein. Okay. And this photoelectric effect was actually in contradiction to the existing theory of light, that light is wave in nature, and this particle theory of light again brought in light the Newton's corpuscular theory of light, when Newton said that light consists of a stream of particles. Next is Young's double slit experiment. Now, Young's double slit experiment actually showed the wave particle duality beautifully by his experiment, just simply by changing the intensity of light from the source. Basically, it was observed that for low intensity, somewhat particle behavior of light was experienced, and for normal high intensity of light, the wave nature of light was experienced. And third is atomic spectra. It was seen rather that the atoms of hydrogen, when they emit light, the light that they emit is not continuous, but it is in short pulses, and those pulses have got definite wavelength. Okay. So, this led to the concept of having discrete energy levels inside an atom, right, because if the energy levels are discrete, only then the energy radiations of a fixed wavelength or some certain wavelength will actually be emitted, and not all types of wavelength will be emitted. So, this is again in contradiction with the wave theory that we have. Okay. So, all these experiments basically led to the development of quantum theory. It was understood that at the atomic level, it is difficult to explain all these phenomena by considering the Newtonian mechanics or classical mechanics, right. The next one, that is the Broglie hypothesis. Okay, we call it de Broglie hypothesis, but it is actually the Broglie hypothesis. And to end this confusion whether light is particle or whether light is a wave, the Broglie actually proposed that all particles of matter which are in motion also has a wave nature in addition to having a particle nature. So, all particles, rather to frame it, all particles in motion which have a particle nature obviously also have got a wave nature. So, this is called the wave particle duality principle, right. And the Broglie proposed that a particle of momentum p equal to mv, or momentum is equal to mass into velocity. So, this is given by lambda equal to h by p, or p is actually mass into velocity, p is mv. So, a lambda equal to h by mv or p equal to h by lambda, right, as you can see on the screen. Now, if we divide both the numerator and the denominator of this p equal to h by lambda by 2 pi, the result is h by 2 pi divided by 2 pi by lambda. H by 2 pi is nothing but it is called h star, also known as normalized Planck's constant. This h star, as you can see, and k is equal to 2 pi by lambda. K is actually called wave vector. So, as you can see that this relation is actually a very fundamental relation in quantum physics. It is an absolute fundamental relation, and we have all done this when we actually read physics. Now comes the concept of quantum mechanics. Basically, quantum mechanics was developed by two scientists in two different approaches. As you can see on the screen, developed from two different approaches by Heisenberg and Schrödinger. Okay. So, the first person, Heisenberg's, utilized the concept of matrix mechanics, and the second person used a wave equation to describe quantum mechanics, and which is also called wave mechanics. Okay. Heisenberg's uncertainty principle, which was given by Heisenberg, it states that it is impossible to measure with absolute precision both the position and momentum of a subatomic particle simultaneously. Very interesting, because in case of classical mechanics, all of us know that obviously it is very certain to measure the position of a particle which you can see, but in the atomic scale you cannot actually determine with absolute accuracy the position of a subatomic particle. One of the main reason for this is that the electron that actually revolve around the nucleus in fixed orbits, they have both a particle as well as a wave nature according to the hypothesis of de Broglie. Okay. So, obviously, the location or the position of the electron from the nucleus, that is not fixed, and that changes from time to time, and it moves or it revolves like a wave. And number 2 is the wave equation. Okay. So, this is the wave equation. This wave equation given by the other scientist describes accurately the motion of electrons in crystals, okay. And this wave equation is actually based on the conservation of energy. Now, electron is treated like a wave. Okay. So, when an electron moves through a crystal, crystals are actually materials with regular atomic arrangement. So, when electrons move through a crystal, then they are described by the wave equation, rather it is a wave equation for electrons, and this wave equation is derived from, or it is based on the principle of the law of conservation of energy. Okay. Now, let us come to the next topic, that is effective mass. Now, what is this effective mass? Now, when the electron is free, okay, on that electron what type of force actually acts? No idea? Well, when an electron is free, an external force can act on the electron, means any force can act on the electron. For example, if you apply a voltage, if you apply an electric field, it can act on the electron. But when the electron is inside a crystal, in addition to the external force, that is when it is inside some material, and if you apply a voltage from outside, then it will experience an external force due to the voltage, as well as it will experience an internal force as well. It will experience an internal force as well. Why? Due to the presence of other atoms, right. So, when the electron moves through the crystal, it collides with other atoms, and therefore, it loses momentum. So, the total force acting on the electron in a crystal is the sum of the external force and the internal force, which is equal to mass into acceleration by Newton's second law of motion. And then you can write like this, that F of external is equal to m star into A. Well, how did I do this? You see that external force plus internal force equal to mass into acceleration. Now, what is this mass? This mass is actually the mass of the electron, the actual mass of electron, which is about 9.1 into 10 to the power minus 31 kg. Okay. Now, after this line, that is, you can see this line, this one, look at this mouse, F external equal to m a minus F internal. Now, what we do is that instead of taking this minus m a minus F internal, we change, in order to take into effect, or in order to account for the effect of the internal force on the electrons in a crystal, we consider the effect of the internal forces, and then what we do is that instead of writing this entire equation, or instead of simply calculating the internal force acting on the electron, we change the mass of an electron to a convenient value, okay, which is known as effective mass. Effective mass means the mass of an electron considering the effect of the internal forces on the electron. And as you can understand that effective mass, basically it is actually not a constant for the substance, because each atom or rather each material has got different atomic arrangement. Now, since the atomic arrangements in each material is different, the effective mass in each material is also different. Although the actual mass of electron is constant, but the effective mass of electron varies from one semiconductor to the other. So, why do we do this effective mass? So that F external can be computed directly. So, we can write this external force equal to mass into acceleration, just like Newton's second law of motion. So, that the mathematics becomes easier. Next, we come to the concept of energy versus wave vector diagram, also known as the EK diagram. Energy versus wave vector diagram, also known as the EK diagram. Now, all of us know that P equal to mass into velocity. P is momentum. So, momentum is mass into velocity, and we have already proved this in the portion of de Broglie. You can check that. Look that we have proved that P equal to H star K. Look at the mouse, P equal to H star K, we have already proved this, where K is wave vector, H star is normalized Planck's constant. So, let us come back to this slide. So, P is equal to H star K. Now, we know that the relation between kinetic energy and momentum is P square by 2m. So, what is this P? P is nothing but H star K. So, it is H star square K square by 2m. Now, if kinetic energy is plotted against momentum, means K wave vector, not momentum, but wave vector, we will actually get a parabolic curve, because kinetic energy equal to H star square K square by 2m. This is actually like the equation of a parabola, y square equal to 4ax. Okay. And therefore, the nature of graph between the energy and wave vector will be parabolic. Now, this K is known as a wave vector, but loosely actually most of the time we refer to it as momentum, because K is actually proportional, rather momentum is proportional to this K, that is the wave vector. So, loosely we sometimes call K as momentum. So, here we have written H star square K square by 2m. What is m? M is the mass of the electron, right. But what should we use over here? Not the mass of the electron, but the effective mass of the electron. That is the mass of the electron considering the effect of the internal force. So, whenever we will talk about mass of the electrons, it is effective mass. Similarly, just like electrons, holes also have an effective mass, right. So, based on this concept, based on the concept of this EK diagram, there are two types of semiconductors. One is a direct band gap semiconductor and the other one is an indirect band gap semiconductor. Now, the direct band gap semiconductor is a type of semiconductor which is used mainly in optoelectronic devices, that is devices that emit light. Okay. For example, LEDs, LCDs, right, mainly LEDs actually. Okay. So, they are basically optoelectronic device. So, how does it happen? In case of a direct band gap semiconductor, the position of the conduction band and the valence band are in alignment, are in exact alignment with each other. So, what happens is that, just to say it qualitatively, an electron which is in the conduction band can directly jump to the valence band, and as a result energy is released, and this energy is in the form of electromagnetic radiation, and this energy depends on the energy band gap, right. So, greater the energy band gap, greater is the energy released, and therefore, the wavelength of the light also changes accordingly. So, we can simply, if we can tune the band gap of a direct band gap semiconductor, we can easily get different wavelengths of electromagnetic radiation getting emitted from the direct band gap semiconductor. And this can be done simply by changing the lattice constant of the material. Some examples of direct band gap semiconductors are basically gallium arsenide, indium arsenide, etc. Now, next we come to indirect band gap semiconductor. So, obviously, indirect band gap semiconductors are the reverse of direct band gap semiconductors. They are poor emitters of light and they cannot be used in optoelectronic devices. The electron transition takes place from the lowest level of the conduction band to the highest level of valence band, but this transition does not take place smoothly, does not take place directly. So, what happens is that the electron jumps to some intermediate state before it comes to the valence band, because the position of the maxima of the valence band and the minima of the conduction band is for different values of momentum, as I will show you with the help of the diagram. Okay. So, directly the electron jumps from the means rather indirectly from the conduction band to the valence band, and the energy that is involved in the transition, this energy is converted to heat energy. Hence, there is no emission of light. So, basically what happens is that this heat energy, this energy as heat is given to the lattice atoms of the crystal and they start to vibrate rapidly as a result of this rise in temperature. This vibration is also called phonons. So, we rather say that when an electron jumps from a higher energy level from the conduction band to the valence band in a direct band gap semiconductor, a photon is emitted, and when this transition takes place in case of an indirect band gap semiconductor, phonons are generated, PHONONS, phonons are generated. Examples of indirect band gap semiconductor are silicon and germanium. This is the diagram for the direct and the indirect band gap semiconductor. So, as you can see, for the direct band gap semiconductor, this is the EK diagram, the energy versus momentum diagram for the direct band gap semiconductor. As you can see that this is parabolic in nature, it is parabola, right. The upper curve indicates the energy levels of the conduction band and the curve below indicates the energy levels of the valence band, and these two energy levels are separated by a energy band gap Eg. So, this is the minima of the conduction band and this is the maxima of the valence band. So, the electron directly jumps, as you can see they are in same line. So, they directly jump to the valence band from the conduction band, and for this there is no change in momentum. But what about this indirect band gap semiconductor? The electron does not jump directly, but it jumps to some intermediate state EF over here. That means the momentum has to reduce, okay, because see the minima of the conduction band occurs for a higher value of momentum than the momentum in case of the valence band maxima. Okay. So, here we can say that as soon as the electron jumps from the conduction band to the intermediate energy state, then it stays over there for some time and then it jumps to the indirect, means it jumps to the maxima of the valence band, thereby releasing heat. Next we come to another topic which is called carrier transport. Basically, carrier transport takes place in electrons both due to electrons and holes, and there are two types of carrier transport. One is called drift and the other is called diffusion. Now, drift is a type of carrier transport which is under the effect of an electric field. So, in this way drift current can be defined as it is a flow of current due to the effect of electric field. So, electrons move opposite to the direction of the electric field and holes move in the direction of the electric field. And the second one is diffusion. We have already learnt about diffusion in biology, right. What is diffusion? Diffusion is the movement of molecules from a region of higher concentration to a region of lower concentration. And how long this process takes place? Unless the concentration becomes same on both sides, right. So, here diffusion current means it is a flow of current due to the difference in the concentration of the charge carriers, right. So, obviously, the electrons move towards the side where there are less electrons and the holes move towards the side where there are less holes. Okay. So, next concept is mobility. So, mobility is defined as the ease with which a charge carrier flows, how easily a charge carrier can flow. Now, if the electric field is very low, then what happens is that this is the relation which is applicable for low electric field. Vd is equal to mu into E, where Vd is called the drift velocity of the charge carriers. I will come to this concept of drift velocity, what is it actually. E is called the electric field. Basically, the drift velocity is proportional to the electric field, and if you equal them, you get a constant which is called, you rather get a proportionality constant, and that proportionality constant is known as mobility. Okay. And the unit of this mobility is centimeter square per volt second. Okay. Vd is drift velocity of charge carriers. So, drift velocity is actually the velocity with which the charge carriers are moving. So, it is very evident that if you give or if you increase the electric field, the velocity of the charge carriers will automatically increase, because now they will be experiencing greater force from the electric field, right. Okay. So, next we come to the derivation of the carrier drift. As you can see that we have a basic relation over here. If we have a, I am just reading it out, if we have a positive volume charge density rho moving at an average drift velocity Vd, the drift current is given by rho into Vd. Now, how to understand this? You simply match the units on both sides of the equation. Okay. J drf, J is the current density, unit is ampere per centimeter square or ampere per meter square. Rho is called the volume charge density, that is number of charge carriers per unit volume multiplied with drift velocity, unit is meter per second or centimeter per second. So, if you find out the units on both sides, you will see that the units are same on both sides, and hence this proves that the equation is correct. Now, this rho is called the charge density, and this can also be written as E into P, right, where E is the charge of one particular charge carrier. In this case, it is maybe electron or maybe hole. In this case, we are considering it for holes, right. So, it is E into P into VdP, where P is actually called the charge density, okay, of the means number of holes per unit volume, okay, multiplied with charge for one hole multiplied with the drift velocity for the hole, that will give you the current density. So, similarly, this VdP is equal to again mu P into E, the same way that we have derived. Drift velocity is mobility into electric field. So, you replace VdP with mu P into E in this equation. So, EP into VdP, you replace VdP with mu P E. So, it is E mu P P E. Okay. So, this is the expression for the current density. So, as you can see that the current density depends on the electric field. Just as I said, since this is a drift current, it must depend on the values of the electric field. Okay. And the same thing can also be extended to electrons, where the only difference in the electron is that the direction of flow of the electrons is opposite to the direction of the electric field. So, this Vdn over here is equal to minus mu n into E. This minus sign indicates that the movement of the electrons is in a direction opposite to the direction of the electric field. And over here at the top, as you can see, Jn drf is equal to minus En into Vdn. The negative sign implies that the charge is negative. So, ultimately Jn drf is positive, E mu n n E. The charge density is positive, although the electrons move in a direction opposite to the direction of the electric field. And this J total, that is the total value of the current density, this J total is equal to the current density due to the holes plus the current density due to the electrons. And next comes carrier diffusion. So, after carrier drift we have carrier diffusion. As we know that carrier diffusion is due to the flow of charges from one point to the other due to differences in charge, or is the density, difference in the concentration gradient. So, this concentration gradient, now if n is the number of electrons per unit volume, then dN by dx, this gives a change, or the change of the concentration of electrons with distance, dN dx. And Jn diffusion, that is this one, the diffusion current density is directly proportional to this concentration gradient multiplied with the charge. Obviously, because they are charged particles, the diffusion current is proportional to the charge multiplied with the concentration gradient, and if you make them equal, you will get another proportionality constant which is called dN, also known as the diffusion coefficient or the diffusion constant, and the unit is about centimeters square per second. As you can see in this diagram, n of minus L, n of 0, n of plus L, these are different positions of the electrons. In n of minus L, the electron concentration is less. Okay. In n equal to 0, electron concentration is slightly more. X equal to L, it is much more. So, the concentration gradient increases as we go in the positive direction of the x axis. Okay. So, the electrons must flow from higher concentration to lower concentration, that is, it must flow in the direction of the negative x axis. Similarly, for holes we can write like this: Jp diffusion equal to minus E dp into dp by dx, where dp by dx is the concentration gradient of holes. Negative sign implies that the direction of flow of the holes is in a direction opposite to the direction of flow of the electrons. Okay. In other words, one way that we can describe is that in Jn diffusion you see that there is no negative sign, right, because the minus of the electron that gets cancelled with the concentration gradient dN dx that we have. The electrons try to move from higher concentration to lower concentration. So, the direction of flow of electrons is in a direction opposite to the diffusion current, okay, as well as the charge on the electron is also negative. So, this minus and minus makes it plus, right. But over here the direction of flow of holes is opposite to the direction of flow of electrons. So, a negative sign has been given. Next we come to the concept of resistivity. Now, resistivity is nothing but the inverse of conductivity. Now, as in this derivation, as you can see, the total current, total drift current is nothing but Jp drift plus Jn drift, and in this expression it is E mu p p plus E mu n n into E. Now, we also know that J is equal to sigma into E, where J is called current density, sigma is called conductivity. So, if I compare equation 1 with this J equal to sigma E, then I must get sigma equal to E p mu p plus E n mu n. So, resistivity is 1 by conductivity, or it is 1 by E p mu p plus E n mu n. This is actually the value of resistivity. So, simply by comparing the two equations, this equation and this equation, we get sigma equal to this. So, rho is 1 by this, and the unit of resistivity is about ohm meter or ohm centimeter. Okay. Okay. Now we have another concept, that is a semiconductor in equilibrium. So, till now we have developed a basic understanding of semiconductors, and now let us move into the actual physics or the operation of the semiconductors. So, first let us consider that when the semiconductor is in equilibrium, what happens? Basically, thermal equilibrium implies that the semiconductor is not in an unstable condition rather, and it is at a constant temperature. No external energy or no external excitation acts on the semiconductor. Whenever there is any deviation from thermal equilibrium, so any deviation will actually change the carrier concentration. So, electrons continuously get excited, thermally excited from the valence band to the conduction band, right. The conduction of electrons from the valence band to the conduction band, that does not stop. But what happens is that the rate at which the holes and electrons are generated, at the same rate the electrons and holes recombine with each other. So, basically the electron actually get continuously thermally excited to the conduction band, and the electrons in the conduction band may fall to the empty states in the valence band, and at thermal equilibrium the generation rate becomes equal to the recombination rate. Generation rate and recombination rate becomes equal, and hence we say that the semiconductor is in thermal equilibrium. This is the diagram for the electron hole generation and the recombination. The up arrow that you can see over here, this indicates electron generation, and the electron that goes to the conduction band after moving a certain distance again jumps back down to the hole, right, and this is called electron recombination. Basically, generation of charge carriers are of three types. There are three types of carrier generation. One type is called photon generation, one is called phonon generation, and the other is called impact ionization. In case of photon generation, when a photon of light falls on the semiconductor, which is greater than, whose energy is greater than the band gap of the semiconductor, this generates an electron from the valence band to the conduction band. This mainly happens in case of mostly direct band gap semiconductors. Okay. In case of phonon generation, increase in temperature increases the lattice vibration, and that leads to the breaking of more covalent bonds, resulting in more phonons. Third is impact ionization. The electrons that move with acceleration under the effect of electric field, they actually hit other silicon atoms. So, when electrons are actually set free due to breakage of covalent bonds, those electrons may hit other silicon atoms, and due to this impact, the electron in other silicon atoms may actually come out. Okay. And this type of generation of charge carriers is called impact ionization, because this happens due to the physical impact of one charge carrier over another. This is the diagram for photogeneration. As you can see, light of energy greater than the band gap is coming, and the electrons are getting excited to higher energy states. It may be so that the electron may reside at the minima of the conduction band, or they may go to higher states in the conduction band. Okay. This is one type of generation. This is phonon generation. In case of phonon generation, you can see that the electrons and holes, these two pairs have actually been generated, right, and hence we are getting current conduction. We are getting new carriers which have been generated thermally. And number 3 is impact ionization, where one electron you can see which is free, it hits a silicon atom and 2 electrons are released. So, one electron can release 2 electrons, and this electron, the actual electron, it loses its energy rather. Okay. So, this has got a cumulative effect, you can say. Next we come to the concept of recombination of charge carriers. Now basically again there are three types of recombination that we will be discussing. Number one is radiative recombination, number two is Shockley-Reed-Hall recombination, number three is Auger recombination. In case of radiative recombination, as the name suggests, radiation takes place whenever there is a jump of electrons from the conduction band to the valence band. There is a radiation of electromagnetic radiations whose energy basically correspond to the band gap. In case of Shockley-Reed-Hall recombination, which is number 2, this type of recombination mainly occurs in impure semiconductors, and here the recombination takes place through some defect levels in the forbidden gap. Number 3 is Auger recombination. Now this Auger recombination mainly happens in doped semiconductors. The energy that is released from the recombination of one electron is given to a third electron or a second electron, you can say, which absorbs energy and goes to some higher energy state. And this is also a form of non-radiative recombination, because otherwise, due to the transition of an electron from the conduction band to the valence band, an energy or a photon would have emitted. So what happens is that photon is absorbed by a third electron and it goes to some higher energy state. This is the diagram for radiative recombination, where you can see that an electron which is at a higher energy state in the conduction band, it falls back to the minima of the conduction band after losing its energy in the form of heat, and then from the minima of the conduction band it directly jumps to the valence band, thereby releasing the energy of recombination, okay, as a photon of light. So this type of recombination, this radiation mainly happens in case of direct band gap semiconductors. Next is the Shockley-Reed-Hall recombination. So in this Shockley-Reed-Hall recombination, you can see that this is mostly applicable in impure semiconductors, where the energy level in between the conduction band and the valence band is not completely forbidden, but there are certain energy levels that can actually come up in between these two levels due to the presence of impurities. So what happens is that an electron that tries to jump from the conduction band to the valence band may get trapped in an intermediate impurity level, okay, and this transition from the conduction band to impurity level and then from the impurity level to the valence band, this may result in the emission of a photon or a phonon. That depends on which type of semiconductor we are using. Number 3 is Auger recombination, the third type, where transition of electron from the conduction band to the valence band results in the release of energy, and this energy is given to a third electron, which then goes to some higher energy state, and then it releases that energy in the form of heat and then again comes back to the minima of the conduction band. So this was all about the concept of Auger recombination. Okay, so hope we have cleared most of the concepts that are required for building up in order to understand the concepts of semiconductor physics. So thank you for listening to my lecture with patience. We have come to the end of module 1. In my next lecture, I shall be dealing with the portion of diodes, and that will be the beginning of module 2. Thank you.